welcome everyone. Myself, I'm Ignas Bagdonas. I'll be telling you a fairy tale about hardware, adventures of hardware in the software world. Now, first, some house rules. As this is the session after the lunch, so please, if you want to take a nap, don't snore too loud, not to wake up your neighbors. Right, and then let's start. So. This is basically a compilation of some random topics that I've been giving to quite a few software engineering groups from the perspective of what's hardware, how to deal with that, and why sometimes what you're doing from a software side of the house doesn't necessarily look right, and why it doesn't work as you intended, or why the performance is not so good. So, if you look at the computer system from the very high above, that's a processor, well, memories of my happy childhood, Z80. Then you have a memory. In this particular instance, you have the inductor memory. Well, I'm a bit too young to actually have worked on that. Right, the slides don't seem to be moving, although they are moving on my laptop here. So why is that? Apologies for that. Right, let's start from the beginning. So if you look from a very high above into a computer system, you have a processor, that's a Z80. So fond memories of my childhood, many happy days playing up with that platform. Then you have memory. This is a little bit older than I am. I actually haven't used that, but touched that with my own hands. And then you have the interconnect system. Well, basically, a rather primitive two-layer board with a few other components. That particular instance is 86RK. Sadly, not the machine that I have built. It actually didn't survive until today, so that's just a picture stolen from a random location in the network, but it was mostly the same. If you go up to today, things have changed a little bit. Processor has got a little bit more pins to talk to the rest of the world. Memory has moved from inductors to capacitors, although underlying fundamental working principle still has the same, stayed the same. And the interconnect, well, that's where the complexity lies, the really scary things, but we won't be talking about that. So, starting with the memory. Dynamic memory is, in essence, a capacitor array. Right, so you have a huge amount of capacitors. Each of the capacitors is controlled by basically field effect transistor, and then that's how you store your bits. The problem with all of this is that this memory is mostly non-volatile. That means if you don't read or write to it at a really high rate of speed, you basically lose the content of it. The other thing, it's a dynamical, it's basically a two-dimensional structure. You cannot just send the address and get the data out. Let's look time-wise how that operates. So first, as you have a two-dimensional array, you need to send in the first coordinate of the array. That's one command. Right? For illustrative purposes, suppose that it takes one hypothetical nanosecond to do that. Then you wait. And that wait time is substantially longer than you actually send the command, right? Then you send out the other component, selecting the column of that selected row. Then you wait again. Why you need to wait? Basically, it's governed by the laws of physics. The charge which is contained in the capacitor, it's not large. Basically, we are talking about a picoamperes there, picoampere range. And in order to sense that, it requires time. The other thing is you have way more of such capacitor cells than you actually have the bandwidth of the data interface. And again, depending on how that is placed en route on the actual memory component, you basically have to deal with far larger length or a number of those cells. This takes latency, but then you can recover that on the throughput side. So you wait again, and finally your data shows up, and that takes not that many of hypothetical nanoseconds. When you are done reading or writing, an important aspect here to remember that both read and write operations are destructive. So basically, if you do something to the content of that actual cell, then you need to restore either the same read value or write in the new value. So that's yet another command for that. Then you wait. This works. Basically, any computer system more or less operates along these lines today. The differences, they are tiny details, whether that's one particular flavor of a protocol or the other, but overall, an operating principle is like this. Where's the problem? The problem is that the overall good put, or actually useful amount of time that you use the bus compared to all the signaling is, well, it's around 10%. And that certainly is not the happiest thing to do, right? Your marketeers will happily tell you that, you know, this particular new memory technology has that bazillions of gigahertz of throughput. But when you do something in real deployment, you actually cannot do that, reach up to that. Well, first thing, marketeers are mixing up frequency with throughput. That's not necessarily gigahertz, that's baud. And the actual data throughput, yes, that is right. You can achieve that rate. The only thing is that the latency until you get that data is prohibitively expensive. So what's actually DDR? DDR stands for double data rate. Basically, you can transfer the actual payload both on the rising and on falling signal of the clock. That's actually only for data. Commands are still sent in what is called the SDR, single data rate scheme. And basically one cycle is required for sending up one instance. And memory addressing is based on basically each command. For DDR, it's 1 or 2. For DDR5, it's 2 cycles. Rows and columns, they have different dimensions. They have some other properties that you cannot just take the incoming address and send it out to the memory module. There's some shuffling involved there, mostly for signal integrity purposes. Now, the capacitors themselves, they need to be refreshed constantly. That means even if you are not reading or writing something that is of value for you, you need to send out specific refresh commands. That takes up that same, both the command address and the data interface. You cannot use that for something practical. Now, memory internally, the size of the minimum addressable unit, that's called a row. Sometimes you might see the term page. That's not the same page as you are familiar with the software side. That's not 4 kilobytes as you are used to most of the platforms. Depending on the density of the memory modules, it can be 1 kilobyte, can be 2, can be half. Some more specialty memories might have slightly different sizes. And if you look at the final module, basically the what is called the DIMM, the same capacity can be assembled from different modules. What does that mean? It means basically that the performance parameters, depending on actual topology of a memory module, will be different. If you do micro benchmarks, you might easily see tens of % difference. If you do fleet-wide performance measurement, it may come up to an order somewhat below the percent, probably up to single-digit % in certain use cases. Right? So if you really care about the performance, you actually need to be very precise of what kind of memory you are using. And it's not uncommon if you are building your software system for some specific hardware configuration or some specific hardware platform, you basically mandate what type of memory geometry will be used there. You can get this data, right? Or you can adjust your data structures then. So why this is important from the software side? So you have your 4 kilobyte page, which you are dealing from a software-wise. Now, this maps into 4 different memory rows if we are talking about a single channel memory. Right? That means that you cannot just jump from one to the other with the same actually access speed. Within the 1 kilobyte range, yes, you just need to send out a new column. That's one command. If you cross that boundary, you need to close the previous page, open a new one, and then start sending another row commands. So if you have, for example, one memory channel, that's quite noticeable performance difference. If you have multiple channels, that's where the address mapping comes into the picture. The way how the actual platform configured, and this is very platform specific, right? Yes, you can control this, but typically this information is available only at NDA contract from actual manufacturer of the specific components. You can actually control which particular bits, how they are mapped from the physical side to the, basically from a physical address to the geometrical address. Basically, memory uses geometrical addressing, and what is coming out from the processor component, that's physical addressing. Typically, it involves some rather trivial to implement hash function. It's deterministic, meaning that if it works for one range, it will be replicated for the other ranges too. It's not, to an extent, it is similar, like, for example, if you have in a contemporary processors, the layer 3 cache, which is segmented. Some lines will be adjacent to your core. Some of the lines will be possibly far away. It's still on the same socket, right? But the latency accessing what looks like a uniform layer 3 cache is actually not uniform. Exactly same is happening with memory, just on a very different time scale. While in the cache we are talking about, say, tens to hundreds of nanoseconds, here we are talking probably one or probably two orders of magnitude higher latencies. And that certainly gets visible and noticeable in the actual performance measurement. Of course, you need to be realistic. You certainly can craft a micro benchmark which will show you, oh no, your platform is really bad at this, right, because of reasons. Now, if you look from a practical point of view, most probably that will get lost in the noise of lots of other traffic that is happening on that same memory interface. Then you have interconnect within the socket. If you have a multi-socket system, that gets even worse because there's a lot of cache coherency traffic going between all the cores and all the sockets. That's probably a rounding error. As a general rule, if you want performance, you have less sockets in the system, right? And of course, you can more or less control that, but anything that goes outside of a socket, that incurs a really noticeable additional latency. So what can we do about that? So that's that previous picture condensed into one small square. It's actually, let's add another layer of indirection, simple thing. Well, we are in the software engineering, we're in the engineering side. So we designate a portion of that capacitor array to be treated as a standalone logical addressable entity. We add another one, yet another one, and well, basically we burn just 2 additional bits, no big deal. What this gives to us is that now we can have 4 independent pages open at the same time. And we actually can send out the commands. It's the same shared command address bus. We send the commands instead of, if we go back a little bit, so instead of waiting here for 10 hypothetical nanoseconds, we send a command to one bank, it does its magic over there. We send command to another bank, does its magic over there. We send command to the third bank. Then instead of 10, we wait probably 6, right? Then we send out the column address, and eventually we're starting to get a flood of data transfers from different banks. Works really nice in theory. The complexity with this is that basically you are talking about a scheduling system. If you have a bank with an open page and you have another request coming, you have 2 requests coming in, one for the same bank, different row, another one for different bank. We don't care about which row it is. Which one do you serve? Because you don't know, maybe in another 10 hypothetical nanoseconds, if you close the first row, reopen it, you will get another 6 requests for exactly the same row which you had open. Right? Trading in some latency will actually give you far bigger throughput at some point in future. So today, if we are looking into a contemporary memory controller, the most complex part and the one which is both from the configuration point of view, all those things are configurable, and from basically power consumption point of view is basically scheduling. Yes, there are clever kind of not branch prediction, but memory location prediction type of algorithms. There's some heuristics that if there is a pattern, maybe we believe that this pattern will continue, and therefore we, to some extent, try to keep this page open. Then let's do it again. Let's logically group some more of such groupings. Yes?
The scheduling, we're talking about the CPU.
No. Memory controller. Basically, this is it's sitting on the same package. So basically, if you look at that first picture with many pins, it's not within the core. It's something that is called the Uncore, basically the entity which is on the same physical package but doesn't do the processing. If you compare that to previous times, take for example PC, the Pentium Pro, it had physical address and data pins, and that went out to other components. This one, yes. Now this one sits on the same package, but the memory controller is logically separate. And that's completely different scheduler thing. Yes, it's configurable. You can feed data to it, how to do that, right? But that's a different entity.
Okay, so it's not part of a core.
No, it's Uncore.
Yeah. Okay, I get the idea. Thanks.
Right, and one of the reasons why you have that many pins on the current packages, besides the power things, right? For signal integrity, you need a substantial amount of pins for grounds and basically distributing the power, is that you have multiple physical memory controllers, right? It's something on the order of 140 signals, which is required for feeding one memory module. Right, and well, that's the reason why you have, for example, 4677 socket and basically close to 5,000 pins on a physical package. So another layer of indirection, bank groups. Similar logic, but this is mostly related to the effectiveness of refreshing. Dynamic memory needs to be refreshed. Well, the exact number is every once in 64 milliseconds you need to read the location, otherwise basically you will lose the content. The capacitors will drain by themselves, the leakage current, and then you will read some random rubbish out of there. So if you have say medium-sized memory module like 120 gigabytes, divide that by the size of one row, what's 1 kilobyte, and you easily get millions of rows that need to be refreshed every 64 milliseconds. If you do that manually by sending a refresh commands, you will consume a substantial amount of memory bandwidth. There are specific commands which work on a bank group level, saying that auto refresh this bank all at once and just do that and tell me when you are done. That's oversimplifying the things. Right, this works. That means that while this is being auto-refreshed, you cannot access that bank. Again, that's the question of scheduling. If you take some risk that this will increase your latency, you actually gain substantial amount of time saved for sending out individual refresh commands. If that's not enough, let's add another layer, right? So far we have been talking in the context of what is called rank. Rank is basically the set of physical components. We can have multiples of those and just burn another bit, which is basically a chip select line. So select one or the other. And this way you can have, again, double the capacity, double the signaling rate sending in the commands, and actually try to approach the theoretical possible maximum of what you can get on a data bus size. Today, protocol theoretically allows for up to 8 ranks. Practically, we don't see that many. Well, it's coming. It's related to signal integrity issues mostly. You might have heard about the various marketing names like 3D stacking or multi-die packages that uses something like virtual ranks, probably the right word would be. where the protocol is amended a little bit, again, to partition the kind of at a subcomponent level. Again, the more you partition this structure, the more control, the more granularity you have in what you can send out, and basically it's amortizing the latency. So let's talk about some more advanced topics. By the way, before I run too far away, any questions, any discussion points? What I would really like to see is basically a bi-directional discussion. It's not me just spreading propaganda to you, right? But you also trying to discuss, raise the questions, interesting points. Yes.
So how much it mean the threshold? So is that control what we control converted to the control to actually do the refresh?
And that's how it's done, because we are talking.
Send commands all the time.
And it does that, precisely that, right? If you attach a logic analyzer to a memory bus, you just see commands floating, but every few tens of nanoseconds, there's something happening there, right? And naturally, it takes up the available bandwidth there, right? So there's no software involved into this, right? The time scale granularity is way below what the actual software can do with this. This is pure hardware. Right. A few selected more advanced topics. HBM, high bandwidth memory. Again, marketeers will come and say that this will solve all your problems because it is wide. Yes, that's 1 kilobit in width, basically 1,000 bits. No, in reality, if you do the math, it's 1 kilobit, but in fact, it's 8 separate channels of 120 each. That means if you actually want to achieve even a theoretical bandwidth, you need to send 8 separate streams of commands. That certainly helps for specific hardware, basically for specific compute platforms. Take for example, GPU accelerator, general purpose type of thing, or some other accelerator which parallelizes easily. Yes, that's a really easy gain performance-wise. Right, just send in parallel commands, you will get parallel results. You need to do some, again, partitioning, how the addresses are located, and another setup for that, but there's no magic substitute for the actual engineering. If something says that it's 1024, you really need to be sure whether that's really 1 times 1024. In most cases, that will be fragmented. So remote memory. That's something that is upcoming and appears to solve many of the practical problems. CXL, Compute Express Link, basically that's a derivative of PCI signaling, which gives you what is lacking on the current existing PCI messaging level. That's basically the coherency. You may have memory which is attached over the PCI interface. Please welcome. You can have a memory which is attached over the PCI interface, even sitting somewhere remotely, and that, from a system perspective, will appear as cache coherent. This is not something that is easily or cheaply doable from the perspective of the currently available, or let's say, historical hardware. Right. Why? Coherency is expensive, and sometimes it can get really expensive. What's the problem? Suppose you have 2 different memory regions. They might be in the same system, there might be an air gap between them, and then you have 2 different cores, well, processors for simplicity. If one of them reads any of those regions, it tends to cache that. Right? It's a local cache copy. If it modifies its own copy. At the same time, if another core tries to read the same location, it doesn't know what the first core did, unless there is a cache synchronization protocol. The simplest one is what was actually used in the first distributed systems, like SMP systems. Right? You query all your neighbors saying, if everyone has this line, flush it. Simple to implement, right? But definitely not good for performance. The current distributed caching protocols, typically they are partition-based, and that there is one entity which is responsible for a fragment of the total address space. And again, that's certain hash function, right? You take the query for the particular address, get the hash out of that. This tells you which particular agent on the system is responsible for controlling whether this particular line or set of lines is cached or not cached. You query that particular agent instead of asking each and every one, right? And that particular agent responds to you. You can actually ask to flush it as a proxy flush on its behalf, or it can tell you whether any other system has that cache line in a modified state. This is a really complex distributed protocol. Therefore, everything that deals with single address space and cache coherency in both logical and physical address space. Logical is more complex than physical. That's actually very expensive. Then another notable topic in the memory technologies are non-volatile memories. Well, basically flash memory on the format of the regular memory DIMM. Which operates mostly with the same protocol with some modifications, and it's actually non-volatile. Beautiful thing for debugging. Right, you crash and you don't need to do anything else. Well, you restart your system and then you have all the last state that was executing in the memory. Right, just read that and analyze. Comes at a rather noticeable cost, performance-wise. It's well, a few orders of magnitude slower than the regular memory. There's no surprise. Basically, the underlying technology is the same as in any other non-volatile flash-based storage. Again, the most complex thing in trying to build such distributed single address systems is how do you map different address spaces at the different layers. Right. So first thing, if you look purely from a software side, so what egresses the core, the processing core which you control, that deals on pages. Well, 4 kilobyte pages, 2 megabyte pages, whatever your platform supports. How then that maps to the cache hierarchy? Because within your core you have layer 1 and layer 2. Everything else is outside of your core. That's within the Uncore, right? You can control that topology to an extent. And basically, you can do this yourself. This is software configurable. Then, whatever exits the socket, that typically gets into the domain of the particular hardware vendor. Right? Some things you can control if you have access to that information, and if the platform allows this, or if you are designing your hardware system, you can actually design in that flexibility. But if you are talking about actually squeezing in the performance out of this is one of the most important parts. How do you define the address spaces, and how do you map particular address spaces in a way that allows for latency hiding? Basically, the main problem with memory is its latency. There's sufficient bandwidth available, right? If you are able to feed in enough of the commands coming in, you will be able to actually realize not 100%, but theoretically above 80–85% is rather easily achievable. But this requires, first thing, a very precise topology of your memory system. Then another thing, it has to be coordinated with the software side, right? So your code deals with the logical addresses. There's a translation layer there. Right, then you actually have to deal with how that particular memory range is mapped into your physical space. Once, multiple times, for what reasons, at what granularity, caching parameters and things like that. It gets complex really quickly. Right, so we are doing on time, not too bad. So that's basically to address your question, core and Uncore, right? All of this machinery, so external memory interfaces, external cross-socket communication, so basically KTI, Intel UPI, and other packet-based protocols between the processor sockets, the PCI bus, and all sorts of memory mapped hardware. All of that is controlled from the component within the processor package that is called Uncore. Right? Plus a layer 3 cache is also sitting there. Depending on the actual components, implementation details are different, right? But that is logically kind of a separate part of well, physically it's the same part. Logically, it's a separate part of the processor. If you have more than one socket, logically it all appears that all the cores are, well, basically within your system. Now, if you look a little bit deeper, there is a different cost. So you're probably familiar with NUMA as a term, non-uniform memory access, that, for example, accessing one channel from one core might be less or more expensive than the other channel from the other core. The same is extended to multiple sockets. While the memory address space looks uniform, the actual latency and bandwidth too properties, they will be different just because the bandwidth available between the processor sockets is frequently many orders of magnitude less than the bandwidth which is available from the actual memory controllers on the local socket. Specialty of practically any caching memory system is that if you want to read something, well, you send out a request and you get that. If you want to write something, typically you will have to read that first and only then write, even if you are rewriting everything. It's called read for ownership. There are certain mechanisms which allow you to avoid that. Another thing, all of the access into the memory goes via all of the cache hierarchy. It's not something that you can easily jump over. There are some extensions, some specific what is called non-temporal instructions, where you can specifically request that this particular memory operation will bypass the cache. Why would you want to do that? Exactly for this once, read once type of a problem. So if you are, for example, collecting statistics, that's something that you probably won't need at the same instance, right? So if you send out that gathered data via your regular cache hierarchy, you will have to evict some lines from the cache, because that's the way how cache works, right? And it might be that you start evicting the cache lines which will be needed in your next instruction, just for basically generating more statistics. Non-temporal store allows you to send out this particular memory request by passing the cache directly to the memory controller. At what cost? If you happen to find that you will need that particular memory line again, you will have to bring it into the cache. It won't be there, right? So this is a software design aspect. Basically, how do you design your system, how it will deal with your data? And kind of trying to lift us a little bit higher from these hardware details, majority of the software performance is related to proper data layout. If you design your data in the right way, basically you help yourself by avoiding a lot of later performance optimization problems. It's way easier. Well, you're all well familiar that 3 weeks of coding save 2 days of design, right? So try to do it the other way. First, design your data layout, how that will map to your memory architecture, then go and do the coding thing. Let's switch to the other part of our fairy tale, the processor. And overall, looking from a very high above, what is a processor? It's a gadget which reads instructions and executes them. Well, that's it. End of presentation. If we look a little bit deeper, instructions need to come from somewhere. They come from an instruction cache. And we will be building the picture here fragment by fragment, and some concepts will become clearer as we go. Right, so we have the cache, because we already know that all memory access goes via the cache. We have a dedicated layer 1 instruction cache. Why they are different for data and for instructions? Because of a very different access patterns. Instructions typically are sequential, right? You just read the stream of instructions and you execute that, unless you do branching, and branching is evil. For data, you basically control what you are doing. Those are very different patterns. Instructions are read-only. Instructions require quite a little bit more of the internal data, basically metadata for internal purposes. We'll come to that. Whereas the data is just storage for the data that you're dealing with. So we are fetching the instructions. In x86 land, instructions are of a variable size. In some other alternative realities, instructions are more of a fixed length. You think that's a major deciding factor? Well, let's try and see. First thing, all contemporary platforms for, say, last few decades, they don't fetch byte by byte, instruction by instruction. They fetch a block. Right? That might be 16 bytes, 32 bytes, might be some other not that small quantity. They take that block and send it out for decoding. But first, the fetch is controlled by the branching. Branching and caching today, if we look from basically practical processor design and engineering perspective, those are two main factors for performance. Right? If your branch prediction works well and if your caching works well, the rest, well, you can live with the rest, because that's where the complexity lies, and that's where most of the performance-related aspects are concentrated. So branching, it gives a speculative hint that the next instructions will come from that particular location. Right? It's a simple life when you just read the code sequentially. But branches in forms of conditional statements, virtual function tables, calls, returns, stack, exceptions, and whatnot, they do happen in real life. And, well, you somehow have to deal with this. Branching, from a concept perspective, is really simple. It's a bunch of tables which record the history. At what address we have this branch instruction, where the call flow is coming to that instruction, and what's the history of where it used to go, and at what pattern. From beginning, that was just a simple array of counters, right? If you happen to follow the branch previously, well, just add one. If you once again follow the branch, add one. If you follow branch, add one. If you fail to follow the branch, subtract one, and that's basically such a counter which shows kind of a hint. So if you have another incoming branch instruction, you take its address, probably do some hash calculation, look up the table, and that table shows you the number, like -2, -1, +2, 0, and so on. And based on this, you make a speculative decision that this branch will be taken, and therefore I don't need to fetch a subsequent instruction, but I need to fetch it from where it is pointing to. And this works today. The only thing is that it's far more complex. It can do, and very efficiently can do, things like, for example, you have the same call site, same branch point, same target, but the condition varies. Like, for example, 2 out of 3 calls it is taken, the third time it is not taken because the data is different. This can easily be predicted, and predicted with mostly 100% accuracy for such trivial patterns. Some platforms, again, that's approximate, hash-based approximation. Some platforms can do, well, somewhat below 10, depth of 10 of such sequences, mostly in a random order. Of course, none of the cores will be able to predict random data. And one of the possible outcomes, which actually results in statistically, well, good outcome, is just to take a random decision. If you cannot predict, you spend cycles, you spend time trying to predict, I'll just take randomly, and, well, you will be correct 50% of the time. So once you understand what the instructions are, you need to decode them. And this is where we get into the interesting domain of the internals. The processor doesn't execute instructions. It executes operations. That's basically internal representation. So today, if we look, well, we have x86, we have ARM, we have Spark, we have PowerPC, we have lots of dead platforms like Titanium. Anyone remember that? Right? Internally, mostly all of them operate more or less the same. And the binary ISA, it's mostly a contract level only. Basically, this is what is stable, and you feed the instruction stream into the decoder. What the decoder does inside, it translates that into another format, which is actually implementation specific. Very well varies with each and every model, excuse me, and generation, right? And the mapping is not necessarily one-to-one. Right, some rather complex instructions, especially in x86 land, may and will result in multiple operations. Like, for example, take the add instruction. If you are adding register to register, that's a simple thing, right? That's one operation. If you are adding register to memory, then you have two options. If you are adding memory to the register, you need to read the memory. If you're adding memory to register, you need to read the memory, add, and write back to memory. That's already 4 operations. Generate address for loading, load, add, generate address for storing, and generate data for storing. Right? All of this is happening on the hardware side. There's no software involved into this. So now there's one widespread myth, especially on x86 land. Yes, x86 has variable length instructions. It can be between 1 and 15 bytes. Well, purely based on the encoding rules, it can be longer than that. But anything that is more than 15 bytes will generate an exception, hardware exception, not C exception. Right? Therefore, if we are fetching sequentially, that's say manageable. But if we are having an incoming branch and that happens, for example, to be on the last byte of the fetch block, that means that we have only 1 byte, but the instruction might be way longer. We need to fetch additional blocks. So typically, platforms, together with branch prediction, they do speculative fetching. In the sense that if we have indication that this branch will be taken, it fetches not only 1 block but a few. There are platforms that in general fetch multiple blocks and do multiple parallel decoding for separate blocks, for consecutive blocks, and even for different blocks. It might be decoding the first incoming stream, and then it might start to decode speculatively the possibly predicted branch. Right? This is all done for latency minimization purposes. Right? If you predict a branch correct, and if you, for example, 80% of time you are correct, you win. The cost is only 20% of the penalty, where you have to flush a few tens of operations that you have predicted in the wrong way. But in 80% of other cases, you will predict right, and therefore you can start executing those instructions ahead of time, even not knowing whether they will actually be needed or not. It appears that it is cheaper to throw away some work than to try to wait when you are absolutely certain that you will have to do that work. So, coming back to x86 decoding, there's a widespread myth that, first thing, it cannot be done serially. Second thing, that it is really complex, and well, basically x86 has no future just because of this. And that is wrong, wrong, and wrong again. First thing, you can, and any credible platform does decode x86 in parallel at the same time for multiple instructions. It's actually not complex on the hardware side. How does that work in a very simple terms? You fetch the block, say 16 bytes. x86 has a regular encoding structure. Some bytes indicate the type of instruction, some bytes indicate the prefix, some bytes indicate whether there is this field present, that field present, some others indicate what size of the immediate, and so on. You have 16 parallel comparators, which all check each and every byte. Is this a prefix? Is this a type indicator? Is this immediate indicator? What is the size of the indicator? You get hundreds of such signals in parallel. Then you have priority encoder. Right? So if this indicates that this is a length changing prefix, and the next byte indicates that this is the instruction type, and 4 bytes out of this we have indicator that this is actually next instruction, then we are right. This is basically that length instruction which does this, decode it. This is happening in parallel. On the hardware side, this is really easy to do. Well, basically, you just have logical gates which do rather simple. It's not even a sequential logic; it's just a combinational logic, right? Which just does a lot of operations in parallel. On the hardware side, this is easy. Well, purely from, say, my experience, doing an x86 decoder, the cost of that is, well, roughly 4,000 logic elements on say, mid-range to low-range FPGA, which is basically definitely not a large cost to take, and that just works. It's definitely not even the most complex, but not even the complex part of the x86. it is slow. No, it is not slow. You can easily, well, right, if your goal is to optimize for speed, you can easily do full x86 decoding on order of, say, 3, 4, 5 cycles. Certainly, if you don't have a goal like that, and then overall, if you're dealing with FPGA-based platforms, it will be an order of magnitude slower, but in any case, that's not a bottleneck. And let's look at the reality. Today, x86 is a dominant platform and will stay for a long time. Therefore, this is not a problem and hasn't been a problem for a long time. Basically, the first parallel decodes on x86, they're coming to P5 times, so more than 30 years ago. So, continuing with our processor diagram. Once we decode all those operations, some instructions will indicate that this cannot be decoded into a few of the internal operations. This needs to operate something like a subroutine. Some obscure instructions like non-memory mapped input-output, string operations, and things like that. Well, there's another myth that, yes, there is this what is called the microcode, and there is a myth that microcode is evil. No, microcode is not evil. It's just exactly the list of precisely those micro operations which are being used, converted from the incoming instruction. It's just a library. Right? So if you receive a particular instruction which cannot be decoded directly into a stream of a few operations, it gets redirected to a particular location in that library, and from that library it comes in the stream of operations. For example, how page faults are handled on the hardware level. You access the memory is not mapped in, you get an exception. Exception handler goes into a microcode and starts feeding the stream, which reads CR3. From CR3 follows the memory, goes into a fifth level page table, reads, goes to fourth level page table, reads, and so on and so on. Basically, it feeds in internally from the processor, from internals of a processor, a stream of operations, which actually perform the page table walk. Gets the actual page, right? Then software gets in, does the fix up what is needed, right? But a lot of that is implemented on the hardware level. Operations are also cached, and if you have a loop, you will translate the loop once, and then you will cache the operations which were formed out of that loop, and then it will be repeated from the cache. Well, this saves the bandwidth of a decoding. Why do you need to save the bandwidth of a decoding? You would want to have as many of the operations decoded and ready for execution as you can. There is a parameter called the width. There's a fetch width, decode width, scheduling width, execution width. Those are all different parameters. Typically, they are not that large, and typically below 10 for most of the practical platforms. Inside the queues of, within the core, it can have a low order of hundreds of the active operations ready to be executed. This is basically the out of order paradigm to which we will come. Right? That it fetches way more of the instructions, converts that to the operations, and holds them in a queue for multiple reasons. First, you still don't know whether you will have to execute those or not. That's branch prediction. Second thing, not all of the operands are available. There are dependencies. Some subsequent instructions are dependent on the previous ones. You cannot start executing something in the middle. You need to wait for that. Then there are all sorts of exceptions and restrictions. So even in theory, if your platform can do that many decodes in parallel, that many executions in parallel, the actual number will be way less than that. If you take the theoretical 6-wide execution core, generally, if that's more than 2, you will be happy on average. Yes, you will have periods, spikes where all 6 execution units will be busy, but that's definitely not the case, unless you do micro benchmarks, yes. For a real world load, that's substantially different. Therefore, you want to do as many of these operations as possible, but the reality is different. It's not always feasible and possible. So let's take another step aside about the code density and how that influences the operation. So you have just a very simple thing. Example, you write a 64-bit value to a memory. So on x86, that results, if I'm not mistaken, in 10 octets, and that will be translated into, depending on what you do, into two or 3 microbes, depending on a platform and some other things. If you look at some other platforms, MIPS, you can say that MIPS is mostly dead. In some specific environments, MIPS is very alive, particularly in the networking field. Lots of specialized network processors are MIPS based. And this results in 6 instructions. Why? Because MIPS encoding rules require that each and every instruction is 4 bytes. Well, as hard as you try, you cannot squeeze 64 bits of payload into 32 bits available for instruction encoding. And moreover, you need to spend some bits to indicate that this is actually this instruction, it does this. So what's happening? The compiler generates a sequence, and that sequence logically takes part of the immediate, adds to one register, shifts, adds another one, and so on and so on. There are 2 problems with this here. And this results in 24 bytes. If your platform fetch width is 16, that means that you cannot resolve this in one fetch. You need to do in 2 cycles. Another thing, here you see that it deals with that same register all the time. And that means that even if I decode this, even if I send this for execution, I cannot execute this in parallel because there's dependency. Right? Before I resolve register 2 value in this, I cannot start this command. I cannot start this before those 2 are done. Right? So this is actually bad for performance. Let's look at some others. Well, RISC-V. RISC-V is basically MIPS re-implemented just because of a severe not invented here syndrome type. Spark, mostly the same, but done in their own way. ARM. ARM actually has learned their homework and done the things in more right way, well, as right as it can be here. Actually, they have instructions which align quite well with this. They actually possibly can be fused, depends on the implementation. At least this requires 4 instructions, and that, if your platform fetch width is 16 bytes, you can easily do that in one go. Now register renaming. If you see in your compiler output that this particular code uses this register, it does not necessarily it does not mean at all that this particular register will be used in reality. Inside of the machine, there are a few hundred of the registers. And what you see from the instruction is just a contract saying that basically I want to have this instruction working on this particular identifier. How those identifiers map internally into the platform, that's one of the most complex part of the contemporary machine. Basically, you need to do conversion from a control flow into equivalent of a data flow. Internally, you just take a register and say that this incoming indicator here will be used as that register. Now, if the next instruction uses the same identifier of the register, it does not necessarily mean that internally it will use the same register. It all depends on the control flow to data flow conversion. And this is the area which actually is one of the most complex in the contemporary hardware platforms. Then you have schedulers. You have a stream of instructions, and you need to resolve the conflicts. Which one goes first? Which can be combined with or cannot be combined with the other? What is your resource utilization load at this particular instance? And so on and so on. That's basically a planning question. Then you have execution units. Quite a few of them in parallel. Different classes of operations go into different instructions, and that's where things get in parallel. Right, and this is mostly the term from a marketing perspective. If you hear saying that this is a 6-wide machine, that means that it has 6 parallel execution ports. Yeah, there's a question over there? No, all right. Execution gives the feedback back into the branch predictors because this is the point where the actual branch results get confirmed. So only here you get to know whether you have taken that branch or not. So this means that if you were speculating, and here we are speculating, and only here we realize that we made a branch prediction incorrectly, we flush everything out and restart from the beginning. That happens from time to time, but more often than not, it doesn't happen, right? And this provides the feedback into the branch predictor, taking that. We have taken this branch, here's an updated count or whatnot, right? And there's another element, load store queue. As we are dealing with speculative execution, but we need to touch real memory, real world, that means that we need to load something from memory and we need to store something to memory. If we do that directly, then we need to undo those operations. Therefore, we pretend that we are dealing with memory directly, but in fact we don't. We have an entity that is called the load store queue, and that is how the external memory, or in general, external world is represented for the speculative execution. For example, you write something to memory. That will be indicated over here as a pending load. And only when the instruction goes to the retirement, when it's confirmed that this is actually executed, only then it gets into the cache. But if the next speculative instruction reads from that location to which you have speculative written, it will get the correct data because it is coming from here, not yet from the cache. And only at the retirement, step by step, you are committing the modified memory operations into the memory hierarchy. You might have heard out of order. It doesn't mean that it is broken, well, sometimes it is, but that's about the paradigm that you may execute instructions not in the order that it was specified as an output from a compiler. The question is, what's precisely out of order when we are talking about an out of order execution? It appears that not that a lot from all the complexity of the machinery, and actual execution is probably one of the easier parts if we are looking into the machinery inside of the core. But you have a stream, basically you have a queue of operations that you have to deal with it. If the operands are ready, send it for execution, and that's it. You have done with that, send it to the retirement, it waits there until all the depending instructions are executed, and you are done. Everything else is mostly synchronous operation in regards with the instruction stream, right? One other important aspect which is related directly to software engineering, address spaces. On the left side, and touching a little bit of layer 1 cache, you are dealing with logical addresses. So basically those addresses that you see in your debugger. Starting from a layer 1 cache and further to the right, you're dealing with the translated addresses, basically the physical world. And that's where it matches with our first story about the memory. That's basically this part of caching and well, other entities that are not shown here, that's dealing with the physical address space. Right, do we still have 5 minutes or, right, we still have 5 minutes. So let's look into one practical example, memory copy. Memory copy happens really, really frequently in the real world for very good reasons. And you better deal with that in a more efficient way. Certainly you can copy byte by byte. You may have some other, say, software techniques which try to be clever, but the important aspect to understand here, software doesn't see the internals of what are happening within the execution core, whereas the execution core may have insight into those things. Alignment, source alignment and destination alignment, the size of the memory that you are copying. Shall you use scalar instructions or particular flavor of vector instructions, or maybe you need to fire up the external accelerator, well, in-core accelerator, out-of-core accelerator. Certainly you can control those things, but that means that you need to basically code for that. So if I'm copying the element which is of this size, I do this. If I'm copying element of that size, I do that. And if the element size is yet bigger, I use the third approach. For a platform, if it has a rather flexible mechanism, it can figure out this by itself. ERMS stands for Enhanced Rep Moves, basically just an x86 Intel terminology. This looks like one instruction, it's prefix instruction, therefore it's a stream of opcodes coming from the microcode ROM. Basically, what it does, it dynamically figures out how many bytes we need to copy, what's the alignment of the source of the destination, where we are copying from, where we are copying to, what's the actual utilization of for example, vector units and things like that. It solves this dynamically inside. So basically, from a compiler perspective, you need to generate one instruction and provide a parameter, right? How many bytes to copy from and when and the count. The rest is solved by the actual platform and solved more efficiently than if you would do hand coding for that. Measuring performance. We are a little bit short of time. Let's skip measuring the performance and discuss one rather controversial topic. The universal binary ISA. So this is ARM, RISC, Power, historic platforms as x86. If we look into kind of a higher level splitting, there's RISC versus complex instruction set debate. Many fistfights have been happening over the decades, and probably for no practical reason. If we look at the reality, all of those platforms are mostly the same now. You might be surprised, x86 still doesn't have 32 registers, at least for now. APX is coming. And whether it will not have 32 very strictly, of course, the stack point is still considered to be within the scope of the general registers. That's much more like 31. But on ARM or RISC-V, you have the register 0, so that's mostly equal. The debate comes into whether this is a load store machine versus the register memory. Remember the example about moving 64 bits to memory. Register memory machine, one instruction, probably two micro operations, just do the thing. Right? Load store machine, first you need to load the thing into the memory, do what you need to do, store things into the memory. Well, at least 3 separate instructions. Generally, from the decoding perspective, we have seen that decoding variable length instructions is not that complex. If we look from the amount of work that we have to do, variable length and densely packed instruction set is more beneficial if you care about the overall system performance. Now, details, flags. Some instructions update flags, some instructions don't. Some architectures depend on flags, some architectures have predicates, some architectures have other means of signaling conditionals to the instructions. 2 or 3 operands, destructive destination or non-destructive operation. What it comes down to, and basically today, the actual different hardware platforms, they are rather similar. And if we look from purely software toolchain maintenance point of view, it might be very beneficial to have equivalent, I'm not talking about the same, but about the equivalent functionality in the binary ISA that has a few conversions to the actual dialect used for a particular platform. But you have one compiler, basically intermediate representation to the binary output toolchain. Then you probably have one instruction selector. You have one low-level optimizer for that. And the end result out of the compiler is something like a universal bytecode, which is not interpreted by, possibly can be run natively, maybe with some fix-ups, maybe with some kind of polishing. An ISA becomes as a hardware contract for such platforms. Right, this topic, well, my favorite, vectorization, I can plan to talk for 20 minutes, well, then it became 2 minutes and we are out of time. That's basically end of my rant here. Now, floor is yours. Comments, questions, feedback, gifts, bribes. Anyone at all? Yeah.
You lost me when you were talking about not guaranteeing access to platform watches. Why would that make you step over there?
Renaming, you mean?
I think so. But does it matter or the just
so if you are talking about architectural registers that are visible from a software side, they are not the same. Right? Some of them have very specific functions, like counter is a very specific register. right? Stack is a very specific register. Internally, they get mapped to something which is internal and probably equal, right? And those are internal implementation details, right? And that is actually one of the problematic points of the instruction set, right? It's not good to have specific instructions which rely on particular semantics of specific registers, right? For example, that same CX register, right? It's used for loops, it's used for string operations, and it can be used for regular logic. So that means that I have rather severe restrictions of how freely I can use it as a signaling mechanism into the machine, right? Because some instructions require it. Right. Was this of any use for you? Or interest? Will you see that you will be able to apply something out of this in your practice? All right. Well, so I think we are officially 5 minutes out of time. So I get penalty points for that from our conference organizer. Well, so if you meet him, please say a good word about me. And then what? Thank you. Thank you for your attendance then. Thanks.